Hello. So thank you for coming to. I think this is our last class, right? This is where the course ends. So today I'm going to talk about some example in the case of the polynomial ring, which exemplifies some of the properties we have seen so far throughout the class. So this is based upon a paper from Javier and Arnold. So it's Javier and Arnold. But it also uses some ideas from Lisa's work. Okay, so let's begin with the setting that we're going to be using. So we're going to take n, and p, three integers. And they are such that they are bigger or equal than 1. Then we're going to take a matrix of indeterminates. That is the matrix of variables of size n times n, and we usually are going to identify the elements in this fashion. So 1, x and 2, so on until x and n. This is going to be x. Okay. Now, we're going to consider a field. So for the usual definition of this determinantal stuff that we're going to work, we don't need like extra stuff about the field, but in our setting that we're going to use about to check and think about F-singularities, we're going to need the field to be of prime characteristic. From characteristic P, and we will also use the P case and F-finite field. F-finite field. Okay, so S is going to be your polynomial ring, and it's going to be the ring of polynomials over this matrix of indeterminates. And we're going to find an ideal of S. So we're going to denote it like I sub t of x. This is an ideal of S, and it's going to be so you're going to take t rows. Okay, so for this, we need t to be less or equal than m and n. So you take t rows, you take t columns. That's going to give you a submatrix of the matrix of variables. That's a t by t matrix. So you can compute the determinant of that matrix. We're going to call that a minor of x. So this is a matrix of p minors x, and that's the ideal generated by all of these elements. Okay, so it turns out that this ideal is prime. It's high. is given by n minus t plus 1 times n minus t plus 1. And so, since this is a nice ideal of this guy, we can form the quotient. And that's S plus this. And this is what we're going to call the determinantal ring. So it turns out that this guy, since this is a parametrical, this is a domain. Not only this is a domain, this is a normal domain. With mathematical singularities. Okay. So now we have a normal domain. What we're gonna do next, we're gonna check or construct. I'm gonna give you a prime divisor of this guy. So now consider another determinantal ideal. But now we're going to consider the t minus 1 minors of x prime, or x prime in the submatrix of x, given by the first t minus 1 rows of x. Okay, so we can compute all the t minus 1 minors of this guy. This guy is also prime, and the type of this guy is n minus t plus 2. Turns out that when we take this guy, the extension of this from, since this is an ideal here to the quotient, it's going to be prime as well, and it's going to be a prime ideal of height 1. So we're going to set p sub t n times n to be the extension of this guy to the determinantal ring. Height of this guy is equal, and we're going to have a divisor, a prime divisor. Now, the next thing, now that we have all of this, laid down, it's time to talk about. Oh, maybe we can talk about first about an example. For instance, notice that if t equals 1, so it's going to be all the 1 minors of the matrix. So it's just that the ID of x when t equals 1 is going to be the irrelevant ideal. It's going to be all the, the variables. And for instance, if m equals n and t equals n, so we have a square matrix, and t is equal to n, so it's the minor of n plus of n times n, which is the only one minor because the matrix is of size n times n. So this is going to be the quotient by a principal ideal in that case. Okay, so what do we want to do? So the objective for today's session is going to be to show that the pair is a pure. So a quick recapitulation or a quick recall of what this means. So first of all, this pair, when this guy is a prime divisor, it is the same. It is the same as the pair. So we are going to consider the Cartier algebra of given by this. So here we put for prime ideal of height 1. So this is the Cartier algebra of the P sub T maps. That is the elements here or all the guys such that this is the bracket. Such that this and this guy to this guy. So they are this ideal compatible with respect to this guy. Okay. That being said, what does it mean for the pair to be F-pure? We can think about it in two ways. So one way is that this thing. Oh, where was it supposed to be? Here? Yeah, I think so. So this is enough to compute all the Cartier algebra. Equivalently, that we can find a surjective map, an element here for some e bigger than 0, such that it is surjective. In our case, that's what we're gonna do. We're gonna try to construct during this talk this guy. Okay, so before we talk about this guy, let's take another assumption. Let's assume that n is less or equal than n. So for matrix of variables, it looks like this, like it is wider than taller. But the same is going to apply for the other case. So it's just like to make a little reduction to our problem. You will see throughout the talk. Okay. So what about this guy? So we want to propose a P, right, such that that holds. So we're gonna do the following. So we have X, this matrix of variables, and now, okay, this will be. So we're gonna take certain determinants, certain minors of this guy. So which minors are there gonna be? So we're gonna take first this minor of 1 times 1, that's it, that is only the variable. Then a minor, we expand the matrix, so it's gonna be this matrix, and we compute the minor of that matrix. So in order to denote that, we're just gonna write this. I'll tell you this is the main diagonal of the matrix. And so you know with respect to which matrix you have to compute the determinant, and so on. So then we reach these minors, which are like maximal minors because they are, you know, the size of the width or of the height of this matrix, and so on. Until that's like the middle part. Then once again, the minors start to decrease in size. We have these ones, like from these upper diagonals, and so on. So to this minors, we're gonna denote them by alpha. So this is alpha 1, alpha 2, and so on. For these guys, we're gonna call them beta, beta 1, beta 2, and so on. And the minors in the middle part, we're gonna call them by delta. Doesn't matter actually how do you index these guys, but so I'm gonna skip that part, but you can just know this is delta 1, delta 2, until you do the proper subtraction of things here to know where the index is gonna end. Okay, so
Maybe we're doing an example 3 by 5, something like that.
okay,
Just to mention where is
the what?
just to mention which ones are the later ones. So it looks like 3 by 5 is real quick.
Okay,
Okay.
yeah, let's do that. Actually, let's do it here. So for instance, here, alpha 1 is gonna be m, alpha 2 is gonna be, actually let me put it in green. Alpha 1 is gonna be m, alpha 2 is gonna be gn minus mh, alpha 3. Okay, so you get the determinant of this matrix, right? Sorry?
No,
you got that.
Okay, so that's until this part, right?
Yeah.
And the betas, the one is going to be f, relative al minus fk, and the third one is going to be dkr.
actually, it's going to be a delta. That one's going to be a delta because all the delta.
Oh, yeah, that's right. Yeah, because it's the size of the
There would be
or the minimum from n and n.
4 deltas.
Mm-hmm.
They're called main diagonals, I think. The bigger three ones.
Yeah, so these are the deltas in this case. Is it clear? Is it clear, Rosalind? No. Okay. So for instance, who's gonna be?
One beta is okay, but how we can understand this is delta?
What do you mean? Like for instance, the first delta is gonna be this matrix of A, H, and O.
Yeah, that.
So you're just like you know, like removing like the elements of this matrix from here to from the left most corner.
But then beta is finished. For example, you know how you can understand that beta 2 is the only part, and after that you should start to define delta.
Okay. So, okay. So the betas are gonna be until
Oh,
Mhm.
I got it, there's no problem.
and the same thing to this guy.
Yeah. Yeah.
Okay, nice.
Thank you.
Yeah, no problem.
Actually, the name is like the ones like on the side, and they're called like the lower diagonals. The ones are called the upper diagonals. And the biggest ones are called the main diagonals.
Yeah,
So deltas are main, alphas are lower, and betas are upper.
yeah, I got it.
Maybe just. Yeah, but this here just because I like the colors. Okay. Ah, it's like the Mexican flag. The only letter, the eagle in the middle. Okay, so moving on, it turns out that if you define this to be Frobenius trace times this guy, this is a Frobenius trace of X, you know, the polynomial ring, not the quotient, times this guy. I didn't define this guy. So this guy is going to be the product of all the alphas. The product of all the deltas and the product of all the betas. Okay. And you take it to the p minus 1 power. This is such that this takes 1 to 1. And so this guy lives here. So we're going to see that this guy somehow you can induce from this map a map in the quotient, which is going to send also 1 to 1, which implies that it is surjective. Moreover, we're going to see that it belongs to this collection. And so we are done. So I want to show that this induces a map in here such that how are we not going to do that? So notice, first of all, in order for the map phi, you know, to get an induced map in this ring, we need phi to be such that it sends this guy in the, you know, with respect to this guy, when the Frobenius push forward to itself. Moreover, we're going to need that it sends this as well to itself, or in order to this property, in order for this property to hold. So we need to check two things. Check that this ideal is a compatible ideal, and that this ideal is also compatible. So we need it will give us, you know, the induced map in the quotient, and this will guarantee us the second condition. Okay, so before
sum is in there,
yeah, okay,
which is not trivial. Well, it's
Yeah.
trivial,
yeah, it's not trivial. But I'll talk about it in a minute.
yeah.
So before that, I would like to tell you a nice property about these guys that will come up later on. So it's better to get it done as soon as possible. So suppose, again, we have n smaller or equal length n, and now, same as before, this is an n times n matrix. I think I will need to make it bigger in order for the idea to be clear. So this is x, this is n, this is n. Okay, so we are going to take a matrix of n times n, n columns and n rows. And we're going to take, you know, the matrix of these sides, which is like the furthermost to the right. So in order to do that, we need to take m columns here. And so the amount of columns on the other part is going to be n minus n. But we are not done. We want to take several determinants, several m minors that will help us in a minute. So you have here a matrix of n times m. So actually, we're gonna fix this guy. So what does this mean? We're gonna add or take a column from here. This column that was here, now it is gone. So instead of n columns, we have n minus 1. So let me put it better over here, so that it can, like, it causes less confusion as possible. So we have here n minus 1, and this one is n minus n plus 1. Now, we're going to define some minors, and it's going to be, so take the I column of this matrix for E between 1, so from here, up until this guy. So we said that it was n minus n plus 1. Okay? This is going to be a matrix. And so we took a column here. So this is an x hat. And we want to form an n times n submatrix. So we have here n minus 1 columns. So we're going to stick this guy to all of these guys. So this is the, if this is what's the x, so we have here n minus n plus 1 things. This is going to be the n minus n plus 2. So x n minus n plus 2, and so on until xn. But we do not want the matrix, we want the determinant of that thing.
Where with the x denote the columns.
Yeah. So maybe yes. It becomes clearer. Okay, is it clear? This is, well, for me it was a little bit confusing at the beginning, but now with colors and stuff, I get a more, a clearer picture of this thing. Okay, so what about these minors? What makes them so special? Well, turns out that if you compute the radical of this ideal, it's going to be the same as taking the T minors of the original matrix, but you see there's no like, this is way too much information here, because we are only having here some M minors, not all the M minors, as in this M, as in here. So we're going to restrict this to the last columns. Okay, so we want to prove that. We're good. Okay, so actually this is true without the radical, but we don't know it yet, or I don't have an argument like as right now to tell you why this is true. But after we have proven all of this, since this is gonna be a pure, we can see that this guy, how to say it? Okay, yeah, maybe let's skip that part for the time being, because later on I will show or recall some of the properties that these lattices have when the pair is a pure. So you know that all the elements of the lattice are, for instance, radical, and so this is like let's say a fake radical, because at the end it's going to be a radical, but for the proof we need it. Okay, so we're going to show this by double containment. So the first part, you notice these are minors of size M. And this guy is the ideal iterated by all the minors of size M. So it's clear that every one of these guys is an element of this guy. Okay. Furthermore, this guy is considering the last columns. Well, we're computing the minors of size n minus 1. So here we have m rows. So in order to compute one of these guys, we need to take one of the rows, and by removing that row, we get n minus 1 rows, and that's the way you can compute the determinant. So you just remove one of them and take the matrix. It's a matrix that you get by the remaining n minus 1 rows and the n minus 1 columns, and that's the determinant. So notice that if you want to compute one of these guys, for instance, this, so you have that the matrix is the determinant of and the remaining columns. So we can use the algorithm or the method, the method called Laplace expansion for determinants. So you can pick any row or any column. For instance, let's take this guy, and you compute like you take this one, and then you take times the minor minus the next one and the other one, and so on. So it's gonna be like a sum over the entries of this guy. So it's an alternating setting. Let's put it here. And some MJs, where the MJs are minors of size n-1 times n-1. Moreover, they are minors that you get by only looking at these columns. So these are elements from here. Nice. Then you take the radical, both sides, but these guys are prime, so. So for the other containment, we're gonna use a version of the Hilbert's Lens test, which is sometimes known as the geometric version, or sometimes it's known. I think like yesterday I found a place where they said that it was the rational version of the Hilbert's Lens test. It's so for the Lens test, you need or at least the one that I know from almost all my life, or my mathematical life, is that for any ideal polynomial ring over an algebraic closed field, so this is going to be the same as this, as a radical objective. So it turns out that there's another version that states that even if you take an ideal, not necessarily in an algebraically closed field, then by taking the zeros of J, but these guys in a Q, we are thinking of the zeros, but extending to an algebraically closed field, and then computing this guy as neutral, then we're going to have still the same thing. So we're going to do that in order to compute the other containment. So we want to show now that we want to show that this that this contained here
I just like actually I can tell you they're not true. But let me use Janeta's level. Because actually what you're about to see, it has nothing to do with K being on the right close. It would be valid over any ring.
Okay.
Actually, because it's just basically an output what we're about to say that it's valid over any base. And that means that both schemes defined it have the same 8 point over any ring.
Okay.
And by Janeta's lemma, actually, that would be the argument, implies that these ideals are the same thing. But yeah, go ahead. If you want to use a nutshell, I can tell you.
Okay, yeah.
Tomorrow, what it works.
Yes, that would be very interesting to know.
I remember when I was writing that down, I thought of doing that, but it was like, why am I gonna, complicate things in myself? If I can use it, yeah, be very good too. Yeah.
So this is gonna be equivalent to so let's say this guy is A, B, and C. So we need to show that the zero set of A is contained in the zero set of B and zero set of C. That'll give us the thing that we want to show. So take for instance. So what do we mean by this? So remember that our variables are a matrix. So we're like the elements of our affine space are this affine space. You can think about it in this way. So this A is a matrix of n times n with entries in K, and it is such that entries in K such that it is going to be equal to 0 for all E, since this is the variety cut off by these polynomials. So that means, going back to the picture, that by taking any of these vectors, and these vectors, no, you don't think about them as variables right now, but as entries, as called entries for the matrix A. So since they are 0, that means the determinant of those vectors are 0. And so the vectors are linearly dependent. Okay. So we want to show that this is contained in here. So this like the standard thing. If it were inside here, we are done. So suppose that it is not inside here. Right. So C was this guy, the ideal of the minors of the last rows, columns. So if A is not in here, that means that there must be some minor of n minus 1 times n minus 1 that it doesn't become 0. So there is a n minus 1 minor of A such that it is not 0. So that means that when you examine these rows in the matrix, these columns in the A matrix, so you can find, let's say, just for convenience, that you took the first n minus 1 rows, and the determinant of that thing is not 0. So that means that these guys are linearly independent. Yeah, no matter what, it's gonna what you put here is gonna the part above is gonna still be with determinant non-zero. Okay, so that means these guys are linearly independent, but when you add any other column, it becomes linearly dependent. So this implies you know that the rank of the matrix A, that is the dimension of the space of columns, is less or equal than m minus 1. And so what happens here? So here, we are taking all the elements. So if you want A to be here, big A, it means that for any, minor of m columns, now you take any one, you don't fix these ones, not anymore. So you take any m columns, the determinant of that thing has to be 0. That's what it means to be a 0 of this guy. But that has to be the case, because the dimension is n minus 1. That's the rank is n minus 1, so take any higher amount of columns, that's going to be 0. So, X element of C, B. And that's the, you know, that is the complete proof of that part. Okay. Moving on, I think I'm gonna let this guy stay here because it's gonna be helpful. Okay, so we're ready to show this part. So it turns out that you take X as in there. You know, X is a matrix of variables. Oh, this was n times n. But then you consider some auxiliary matrices. So, for instance, J, Y is going to be the first n minus 1 rows of X. Z is going to be the last n minus 1 rows of X. So for Y, you're considering this part, and for C, you're considering this part. And W to be the middle. I'm just going to denote it by the intersection. That is the columns, the rows that have no, all the rows, exception, you remove the first one and the last one. So there is also like a similar proposition for similar to what we just did. And it says that this guy plus this guy is going to be this with this. And again, we use radical. I'm going to skip the proof of this, but it's the same idea that we used just before. You can say that these guys are minors and that are going to be in these places, like this one by definition, and this one by a Laplace expansion argument again, and the other containment by Nusselen-Schatz or Jonas Lem.
Yeah, I'm not so sure. Because you're using an algebra that I'm not pretty sure to what extent it's true over an arbitrary ring.
Okay.
But it's true over an arbitrary field, for sure. But yeah, but if it's true over an arbitrary field, in principle, that means that the Lushta should imply quality. But yeah.
So why is this going to be helpful? Well, so we want to see, remember, that this guy is an element, it's a phi ideal. But, so what about if we prove that this is a phi ideal and that this is a phi ideal? So remember that the sum of phi ideals is again a phi ideal. Moreover, the radical of a phi ideal is also a phi ideal. And these guys, this is prime, this is also prime. So these are the associated primes of this guy. And the associated primes of this, and a phi ideal is again a phi ideal. So we reduce the problem of finding that this is an element in Q to finding that these guys are phi ideals. So what's different? The difference between this and this, just the amount of rows. You have one less row here and one less row here. Okay. So again, we do the same trick. If you want to prove that this is a phi ideal, you put this one in this place, and you can like reduce again one row on the top side and one row on the downside. So you just are gonna keep doing this until you get to the team. So So we reduce our problem to proving that IT of a matrix X is the ideal for any matrix X tilde of X of T adjacent rows.
That adjacent part is very important. Actually, I don't think it's true if you remove adjacent. I don't think they're compatible actually. I remember, I think there's an example that. Yeah, like. Yeah, it's just like the adjacent part is kind of weird. Like, there's a wide adjacent, why do they remove it? But I think you cannot remove that part. But yeah, go ahead.
Okay. So furthermore, turns out that we don't need, so this problem reduces to only matrices of T rows, adjacent rows of X. So you can reduce even more the problem. So for instance, let's take, you know, a matrix X double tilde of T adjacent rows. And suppose that this matrix does not contain nor the first nor the last row of X, so it lives in the middle in some place. So we know that this guy actually like this. Yeah, this is a bad choice of, let's say, X double prime. So X double prime so what do I want to use here? Again, this decomposition. So here, remember, you have X, and then you remove the first and the last, and you get this one. So now I'm going to do the following. Remember, this doesn't have the first nor the last, so you can add like the next adjacent row. You know, you can add in the top side of the matrix, and the next adjacent row, thinking in the that's downmost or the bottom part of X. So it's going to be the radical. This is T plus 1. T plus 1. So what we are saying here is that if your matrix doesn't contain the first nor the last, say this is the matrix of the two rows, then by adding, you know, the next one, these are this one and this one. So if you prove that these guys are phi compatible, then again, this one is going to be phi compatible. And by taking this process, at some point, you're you know, adding rows from this side, so you're going to reach some point the top part. And here you're going to reach at some point the bottom part of X. So it's saying that the only thing that matters is to prove that the matrices of T rows, of the adjacent rows, but which are the first t ones or the last t ones, are enough in order to prove that any other one in the middle is p compatible. We're doing so well. With all of this, so we'll reduce the problem. Check. That is SP compatible for the first or last t rows of x. So actually, I'm gonna just like take a shifting of the indices. So, and what we want to do is show this, but for the case when x is a matrix of t minus 1 rows. And the ideal, since we are taking the shifting, so we're going to take this guy. Turns out that since we are taking only two cases, the first t minus 1 or the last t minus 1, the construction, or I mean, in order to prove that, since phi is this times this, we only need to check it for the first ones or for the last ones because of the symmetry. So we're going to do this only for the first ones. So we need to show this. And that's the last part of the proof. Okay. So remember, this guy is a prime ideal. So we want to show that. So that's the same as saying that phi of this, the Frobenius push forward of this determinable ideal is contained in here. Again, since this is a prime ideal, we can check its containment in the local, locally. So we localize by this term. We want to see that is false. And this is just in the localization, so maybe think about it, but like this. Or, just extend them to this range. Okay, now, remember that we said, I erased it, but we showed that this was true.
Yeah.
So we are here, instead of using m, we're going to use t minus 1. So t minus 1 plus 1, so it's going to be this. that this is the same as this times another matrix where with this were like the last columns. So you localize both sides, this is gonna go away because these are minors of size t minus 2. So they are smaller, they do not link here, the minus of t minus 1. So that means that locally, this guy looks like that guy. And remember that the height of this guy was equal to exactly this. So it's a system of parameters in the local ring. And so this problem of checking this, it's now reduced to checking that, you know, since, and moreover, since this guy here, remember, was the trace times this guy, so we only need to check that this guy is an element of this ring, of this quotient ideal. So we want to prove that. Okay, so this is the last. Time for this. Have you ever? No. I wanted to. Okay. I'm not gonna say them, but these are very. I think they're pretty cool identities for determinants, and that's gonna make us, in this situation, are gonna make our life like way easier. So for the time being, I'm not gonna say them. I'll state some stuff that is a consequence of these identities, and if there is time at the end, we can like discuss them because it's like it takes. It's not that much time, but it's you know, like a considerable amount of time. Okay, so turns out that we're gonna construct these guys. So if you multiply this beta, remember this guy, times this guy, depending on the power that you put here, we are gonna get some, you know, nice determinants, which are a consequence of this. So for instance, if you put the 0 one, well, you don't get anything. So I mean, this is non-existent, so it's the same one. And we're gonna say that this guy is, you know, the same. Let me just skip it. So it's gonna be clearer, more clear. Is it clearer or more clear? The right word. Clearer? Clearer? Okay. It's gonna be clearer with these higher powers. And then we can move back to this case. So as this increases, this one as well. So we have -1, the 0, +1. This one stays. but the power also increases. And this is gonna be the same. This is by Sylvester's. It's gonna be as if you like take a matrix where these gammas are the ones that we wrote down there. Here is some other things which are not important at the moment. If you keep going on, this matrix gets bigger. And as I said before, here are non-important things. So for this case, it's gonna be just the rightmost upper column, upper element. Okay, so we're gonna call these elements gamma. So this is gamma 0, this is gamma 1, and this is gamma 2, and so on. So you see, the thing here is that these gammas are going to be depending of. Oh yeah, it doesn't matter right now. Okay. Yeah, so let's keep going. So what about these gammas? So, for instance, remember that this guy, since it is a minor of t minus 2 size, it is not an element. It's an invertible element in this ring, because here we are considering like t minus 1, and this one doesn't belong there. So you can like take this one, put it right here, and you have that. This guy is, well, this is the same. There's no extra steps needed to be done there. The next one is gonna be this. This is gonna be beta t minus 2, but powers 2, and so on. So you have this. We said that this is the product of the alphas, the deltas, and the betas. So it's gonna be alphas. The betas now are gonna be gammas. So gamma 0, gamma 1, gamma 2. And here you have beta t minus 2. You just like keep adding the powers. 0, 1, 2. But this is gonna end at some point. And where does it end? So turns out that you take all of these betas, but also we're gonna take these guys. So it's strange. We can discuss this part of the proof later on. But the thing is that you're gonna consider these deltas now as rename them as some betas, but so here you add like the identity matrix and the zero matrix over here, so that when you take the determinant, it's this times this, and this, but it's zero, and this is identity, so it's going to be the same determinant. So just like an auxiliary determinant or construction in order for these identities to hold, because these are for square matrices. So you get like so we remove the deltas. It's gonna be like gammas, and you get this. Turns out that if you take these guys to the p minus 1 power, some funny stuff is going to happen. So, for instance, this guy, we know that this is just n minus p plus 2 and p minus 1. What about the next one? So, it's here. So it's going to be a binomial where we focus our attention on the gammas. So here we have like this power, these coefficients doesn't matter at all, but this is going to be like the sum has to be p minus 1 when we expand this guy to the p minus 1 power. And so if we check this like we check this in modulo, n minus 2 plus 2. Good. So this is gonna be 0 if you multiply by anything like that has at least one of these guys, because then it's gonna be an element of the ideal. So here there is one of these guys. So if this guy is not 0, that's gonna die. So we're forcing this guy to be 0 and this guy to be p minus 1. And so you get that the next part is like this. Okay, so now we have the next one, right? So it's gonna be the same as well. The only possibility is that this guy 0, 0, and this p minus 1. And so on until you reach the first one. Okay. So these are the same modulo that IG. Okay. So what's the cool part about this is that now remember that we have this. So multiply both sides by this guy. So by multiplying by both sides by this guy, you get delta on one side, and you get this thing on the other side times some extra stuff. So you have the and you write it over here. You have the delta gonna be the same as these alphas, these betas, some other coefficients that appear here from related to these guys, but it doesn't matter at all. Yeah, it was here and these guys. Okay, so remember this is a unit. So thinking about this guy as this in here, you see that if you multiply delta by any element of this curve, you're gonna get what we need, right? So we're done. Okay, so now we have that both of these guys live here, and so the sum is gonna live here. And as I said before, that was enough in order to show that the painter is F here. And so we're done. I want to do more stuff, but so because in addition for it being F pure, it's gonna be purely irregular, but that's like 2 or 3 more classes. Okay.
So I would like to give an open problem. So essentially, Pedro today showed that a whole bunch of prime ideals belong to ISP. I claim that there is no other ideal that could be found that is there. But we don't know that. So essentially what would be the statement that all determinant ideals of any set of adjacent rows of any matrix whatsoever is in that IS comma P. So, but I would like to know all of them, but I don't know how to prove that these are the only ones. Yeah, and that has some cool consequences actually in the few problem bases and stuff. But yeah. Next week, Lisa Sesha is going to be here. And Polish is going to be talking about similar stuff, and she has some ideas along those lines. So I recommend you to go to her talk on Monday. But yeah, cool. Thank you very much.
Yeah, you're welcome.